Second hour of Physics 1C, 1B for December 1st. This is section 1377. We're going to continue talking about standing waves. I mentioned some of the features of these things, and one of the features are these things called nodes. The other feature is antinodes, the points at which the amplitude of the string motion is the greatest. So this point is basically going to oscillate up and down and up and down. We call that point an antinode. All right. So let's see if we can understand something about how these standing waves work. So as I said, when you have a standing wave, what's going on is that you have some kind of a string. You send a pulse down in one direction, right? Or more specifically, you send a continual pulse traveling down the string. And what happens is that when that pulse reaches the end, when that wave reaches the end, it automatically phase inverts. And the reflected wave is going to come back. If you produce a standing wave properly, it's going to come back and it's going to perfectly kind of either add or cancel to the wave. And the effect is going to be that when this return wave, which is coming back in this direction, encounters the original wave, which was moving in the forward direction, well, there's going to be certain points like here and here where the amplitude of the wave was 0, so it's still 0. Those are the nodes. But you're also going to have points on the wave where you have cancellations that occur like here and here. And because the waves are constantly moving, those points will actually just kind of oscillate up and down like this, exhibiting constructive interference. So let's look at how this works. So there's going to be a transmitted wave. This is going to be the wave that you send down. That's going to be this one here. This is going to be the transmit, the one that's going this way. And it's going to have we can use the same equation we used for a regular wave, which was you take the amplitude of the wave and you multiply by like a cosine function, and you have like a kx minus omega t, which, just to remind you, k is equal to 2 pi divided by lambda. We're going to need to use that here in a little bit. And then you're going to have the reflected wave. And that one's going to look like, we call this maybe y1 and y2 or something. Y2 of x and t is going to be something like, it gets a phase inversion, so there's going to be a negative sign. And then you're going to have a times the cosine of, in order to get the wave to travel to the left, you just have to put a plus sign in here. But now the transmitted wave and the reflected wave will have the same amplitude, just one is opposite. They'll have the same frequency, omega, and they'll have the same wave number, k. It's just that one has a positive velocity and one has a negative velocity, basically. Right? This is the reflected wave here. And what we can do is we can get the total wave is going to be the sum of each of these, right? So the total wave, y, is going to be equal to y1 plus y2. This is our principle of superposition. So if we add those two waves together, if we add those two waves together, we're going to get this. Y equal to we get that. We can group some terms here. Well, just one. We can factor out the amplitude. So we have amplitude times cosine of kx minus omega t minus the cosine of kx plus omega t. Now what I'm going to do is I'm going to use a trig identity, which is that if I have the cosine of, we'll use a and b, a plus or minus b, this is equal to cosine a cosine b minus or plus. So if it's plus, it's negative. If it's negative, it's plus. And then it's sine a, sine b. So that's two different identities that we want to use to plug into this. So let's do it. So we've got a times cosine kx minus omega t. That's going to be like the minus sign portion of this. So a is going to be kx. So we'll have cosine kx. The b is going to be omega times t. So we'll have cosine omega t. And then when it's negative here, it's going to be positive here for the sine term. So we'll have sine of kx, sine of omega t.
minus, because there's a minus sign right there, we'll open a new parenthesis. Cosine of kx plus omega t is going to be cos kx cosine of omega t. And then when this is plus, it's going to be minus sine. So we have minus sine of kx and sine of omega t. All of that right there. Now, if we look carefully at what's happened here, I believe that this term, due to this minus sign, is going to cancel out with this term. And then we have sine of kx, sine of omega t, minus minus, the same thing. So when we add those together, what we get is 2a sine of kx multiplied by the sine of omega t. And this is going to be the equation for a standing wave. And we can prove, using this equation, where the nodes will occur. Okay? Time is going to be moving constantly, but x, what is x? So if I have a standing wave, right, that means that I have two fixed points, right? And my standing wave, as we saw, looks something like this. It just kind of oscillates up and down. Now, the x direction goes this way, right? The y direction goes up and down. And let's say that I call this point here x equal to 0. If I plug in x equal to 0 into this equation, I'm going to get the sine of 0, which will mean y is going to be equal to 0 at x equal to 0, right? So that means that y of 0 comma t, right, is equal to 0 for any time. That proves that this point right here will be a node, right? Because y is equal to 0. That's where the nodes occur, right? So that makes this a node. This would be the first node. But where do the other nodes occur? Where do the other nodes occur? The other nodes are going to occur anytime y is equal to 0. So the nodes occur at y equal to 0. So if we set y equal to 0 and we look at our equation, and we realize that the time can take on any value we want. So at t equal to 0, for example, the whole wave is going to be flat, right? But as time moves along, right, this will take on any number of values between -1 and +1. This one, however, will have specific places x where the sine of kx is equal to 0. And those points are going to be where the nodes occur, okay? So if we say let sine of kx be equal to 0, this will allow us to find the x location where y becomes 0, which is where the nodes are. I'll stop for a second. Does that tactic make sense? If we want to find where the nodes are? All right. So when is sine of k times x equal to 0? At what values of x will sine of kx be equal to 0? It may actually be easier to see x equal to pi over k. X equal to pi over k. So if we put x equal to pi over k, then what we get is the sine of pi, right? And the sine of pi is equal to 0, right? So that's one answer, right? I think personally this is a little bit easier to understand what the answer is if I put sine instead of k, if I replace this with 2 pi over lambda, because ultimately we want to get this in terms of lambda times x is equal to 0, then this might be a little easier to see. So what values of x? There's more than one. It's not just one value. There's more than one value. What values of x are going to give me 0? Pi plus k. I don't think so. Pi and k? No. What does x need to be equal to make this thing equal to 0? When is the sine equal to 0? We know the sine is equal to 0 if you do the sine of 0, that's 0. The sine, when's the next time the sine is 0? Sine of pi over 2 is not 0, but the sine of pi is 0. The sine of 2 pi is 0. The sine of 3 pi is 0. You kind of figure out what the pattern is here, right? So what values of x are going to make this whole thing equal to 0? Anyone come up with a general statement? In general, what are the series of values x? We basically need this part, right, to be equal to 2 pi over lambda times x needs to be equal to what? What does that whole thing need to be equal to? Needs to be equal to 0 or pi or 2 pi or 3 pi, right? Would you all agree with that statement? Okay, well then it's easy. All we got to do is just isolate x in the same way that we always isolate x, which is multiply both sides by lambda over 2 pi. And what we'll get is x equal to, the first term is going to be 0. The second term is pi over pi, so lambda over 2. The next term is 2 pi over 2 pi, so just lambda. The next term is going to be 3 halves lambda, right? Dot, dot, dot. In general, x is equal to n lambda divided by 2, where n is equal to 0, 1, 2, 3, etc. Okay? That is where you're going to have nodes. Does it make sense? Every half wavelength, you're going to see a node, basically. Okay?
Any questions? I think we can do one problem now. Should be right here. A lot of questions. A lot of questions, but it's not that hard. Okay, so our problem says, a guitar string lies along the x-axis when equilibrium. The end of the string at x equal to 0, the bridge of the guitar is fixed. A sinusoidal wave with an amplitude of this and a frequency of that, corresponding to the red curves in figure 15.24. I think I included that figure. I did not include that figure. Well, we're not going to worry about it because I think it's kind of large. Anyway, okay. Oh, I can zoom in just a little bit more. Okay. Okay. Travels along the string in the negative x direction at 143 meters per second. It's reflected from the fixed end and the superposition of the incident of the standing wave. All this stuff is basically to say we have a standing wave. This is the frequency. This is the amplitude. And this is the speed. Those are the three things we're going to need to know. We want to find the equation giving the displacement of a point on the string as a function of position and time. Locate the nodes. Find the amplitude of the standing wave and the maximum transverse velocity and acceleration. Okay. So, how do we want to do this? It's saying that the waves are traveling in the negative x direction, right? So let's draw our guitar. Do I have to actually draw a guitar? I don't want to. I'm not going to. We have a string. And there is a standing wave that's produced on it. I don't know how many waves are actually going to fit in here. We'll have to figure it out ourselves. They should be equally distant apart. They don't look that way. The amplitude is A. The frequency is 440 hertz. They don't tell you, but 440 hertz is, I don't know, I think it's like an A note. And then, what else do we know? We know it's traveling in this direction with a velocity that's equal to 143 meters per second. All right. Part A says, find the equation giving the displacement of a point on the string as a function of position and time. Well, we already kind of have that equation, and it's this one. The equation for the standing wave was 2a times the sine of k times x multiplied by the sine of omega t.
So that's our equation. And we need to find what these values are and plug them in here. Okay, so let's do that. So y is equal to 2 times a. The amplitude is 7.5 times 10 to the minus 4 meters. Then we do sine of k times x. Well, we need to figure out what k is. And if we have velocity and frequency, can we find wavelength? How do we find the wavelength if we have velocity and frequency? What equation do we use? I know it's late. I know a lot of v over f. There you go. V equal to lambda times f is the equation we want. We solve this and we get the relationship that Louis put in there, which is v over f. That's right. So if that's what lambda is, then what's k? Well, k is equal to 2 pi divided by lambda. So let's solve for both of these, because I think we might need to know what lambda is later on. So let's see. So lambda is going to be, we take our velocity, which is 143. Don't worry about the fact that it's negative. We just care about the absolute value of the velocity. The frequency is 440 hertz. This is going to give us the wavelength. 143, oops, delete. 143 divided by 440. So I get 0.325 for the wavelength. And if I plug that into this equation, we can find the wave number, k. So we do 2 pi divided by that. I get 19.33. And that's going to be in radians per meter. That's the unit we use for k, radians per meter. So plugging that into our equation, we were doing 2a sine kx, right? So now the k is 19.33 radian over meter times x. And then sine of omega, well, omega we can figure out as well, because if we have the frequency of 440 hertz, then omega is 2 pi times the frequency, which will be 440 times 2 pi. So 440 times pi times 2 is 2764. 4 rad over s, radians per second. So in our equation here then, the sine of omega t is going to be the sine of 2764 radians per second times t. That is our equation. Only thing else I could do to simplify it is I can multiply that 2 there and we would get, 1.5 times 10 to the minus 3. We don't need to worry about that. Okay, next says to locate the nodes. Part B says locate the nodes. I noticed one thing about this that's very strange. This is a guitar that has a string with an infinite length as far as I can tell, because it doesn't tell you how long the string is. So when it says to locate the nodes, I guess we just assume that this wave goes on forever, which doesn't make any sense really, because a standing wave has to have a specific length, but whatever. It's a problem from a physics book. It's no surprise that there's missing information. All right, so locate the nodes. Well, we saw before that the nodes occur at x equal to n lambda over 2. So that's going to be, there's going to be a node at x equal to 0. There'll be a node at n lambda over 2. So lambda is this, right? So we do 1 times lambda over 2. We'll have 0.325 meters divided by 2. And then if we do just lambda, this will be 0.325 meters. And then if we do the next one, we 3 halves lambda, so 3 over 2 times 0.325. And solving for these, we'll get the location of the nodes. And you're all more than welcome to calculate these yourselves. I don't think we have to actually do the calculation. Part C, find the amplitude of the standing wave. We already did that. The amplitude is just basically double 7.5 times 10 to the minus 4 meters. So this is going to be 1.5 times 10 to the minus 3 meters, I think. Right? That's right. Yeah. Okay. The maximum transverse velocity and acceleration. Oh boy. Okay, well, now what do we have to do? If I want to find the transverse velocity
And the transverse acceleration, what do you all think?
What do we need to do? Derivatives of y, that's right, exactly. Okay, so if we take the partial of y with respect to time, this is going to give us v sub y. So if we do that, we're going to have this quantity is going to come out of here, and the sine is going to become a cosine, so we're going to get 1.5 times 10 to the minus 3 meters multiplied by 2764 radians per second, and then times all this stuff again. But there's going to be a cosine. Okay, so it's going to be sine of 19.33, and then the sine will go to a cosine. And then you do it again to get the acceleration, and I'll leave that for you to do yourself. You just take the derivative again.
That's all you got to do. Oh, you know what? Actually, all we have to find is the maximum value, right?
So I should be more clear about what we have to do here. This is Vy as a function of x and t, right? But to get from here to get Vy max, all we have to do is just look at the part in the front right here. So this is just going to be basically equal to the amplitude, or 2 times the amplitude that was given, multiplied by omega. And then to get ay, the acceleration in the y direction maximum, this one's going to be equal to 2a omega squared. Because basically this is omega, and every time you take a derivative, you get that omega squared out. And since the maximum value of this is 1, the maximum value of that is 1, the maximum value of the function is just going to be the thing that's out here in front.
Okay. The final topic for tonight is to look at what are called normal modes. I should stop for a second. Does anyone have any questions about this problem? Okay, final topic we call the normal modes
Of the waves on a string. So normal modes. I don't know why physicists love to use the word normal so frequently. It's a word that even in sociology doesn't mean anything at all. It's just normal, but I don't know. Why don't they just call it just the modes on a string? Because that's really what they are. Who knows? Regardless, this is what we call them.
Okay, so we saw that there's going to be this situation that occurs
Where if I have a string and it's fixed at 2 points like here and here, I can produce a standing wave that has a wavelength of about 1/2 of the wavelength of the string, or exactly 1/2 of the wavelength of the string. And when I do that, what I'm going to tell you is that we're going to call this the fundamental mode. We're going to call this n equal to 1. And we're going to say in this particular case that the wavelength is equal to L over 2. All right? The next mode, which we're going to call n equal to 2, could be on the exact same string, but maybe you're just oscillating it more quickly and you find a new mode where you find that it is exactly one wave that fits on the length of your string. By the way, L is going to be this length right here. The length for all of these, L is going to be the length here. So in this case, lambda is just equal to L. We call this one the second harmonic. Mostly because this stuff originated in music. That's why we call them harmonics. And it is second harmonic mode, you might say. And this is going to be n equal to 2. So first mode, second mode. This is also referred to as the first overtone. So you got to get kind of used to this kind of language. I'll talk about what overtones are here in a second. So this is n equal to 2. We keep going up the line. We take our fixed string on both ends, right? And now we start oscillating it just a little bit more quickly, and eventually you find that there's another mode that occurs where I can fit not just one wave, but 1.5 waves on here and set up a standing wave. In this case, lambda is going to be equal to, well, you all tell me, what am I going to write over here? In terms of the length L, what coefficient needs to go here? What kind of fraction do I need to put here? For the first one, we had 1/2 L. For the second, we had 1. You all got it very quickly. Thank you. That's really good. 3/2 L. I love that when everyone's paying attention and gets it really quickly. Okay, so this is, of course, going to be n equal to 3. We call this one the third harmonic mode. And this would then be the second overtone. What's an overtone? Does anyone here play music? Tori, you've heard the phrase overtone before? What's an overtone? It's notes above the fundamental. It helps to create timbre. Yeah, that's right. That's right. What's timbre? Can you say more about what timbre is, Kate? The unique sound of an instrument or a voice or something, right? So timbre is something that you have with instruments, right? Like flutes, guitars, pianos, right? Well, I would say that the difference it's not just different. Okay, I mean, yeah, trumpets sound different, right? Yeah. Trumpets definitely sound different than pianos, right? Even though they're playing the same note, that's right. But to go a little bit further, if you were to take a computer, right, and generate a pure tone, okay, just give you an example here. The frequency of 256 hertz, okay. This, does anyone know? Do you know, Kate? What is 256 hertz? Do you know what that is? Middle C, that's exactly right. Middle C on a piano, so you know quite a bit about music. Middle C on a piano corresponds to a frequency of 256 hertz. And you can produce that same note with your voice. You know, people can sing and produce a middle C note. You can produce it with a trumpet or something else, and all of them will kind of sound different from each other. But what will really sound different is if you go to a computer and you have a computer produce that note right there, what you'll find is that the computer note sounds, I don't know how to describe it. I was looking for a way to show you this earlier, but as I was pulling up things, I couldn't get the volume to work on the stream. I don't know what's going on to where you can hear it. But when you make a computer produce a note like this, it will sound very pure, but it will also sound completely different from that same note produced by a piano. And the reason why is on a piano, when you push the button, what do you call them, the keys on the piano, there's a string that's hit by a little hammer, and the string starts to vibrate. It vibrates just like this. And the length of that string is going to correspond to a frequency associated with middle C. Okay, and you can even figure out what it is. We'll do that here in a second. But what happens is the string itself does not just vibrate only in this mode. It also actually vibrates in the overtones as well. So it vibrates in this mode, it vibrates in this mode as well, and the result is that the sound sounds more full because it's a series of notes that are like middle C and then one octave above middle C and so on and so forth. And so the combination of all those things playing together, all these things playing the same note, gives you this kind of fullness to the sound. And that's what an overtone is basically. It's the difference between like digitally produced music and music that's produced by like string instruments and stuff like that. Someone in my class on Monday said it's the difference between EDM music and like going to a country music festival. That the country music festival might sound a little different than the EDM music.
Anyway, so one other part about this, I guess, that I left out that maybe is
Not so obvious.
here. We'll do the math. I'll show it to you through math. I could show it to you through the musical theory, but we'll just show it to you through math. Okay, so what's the theme of what's happening here? We have the fundamental is half of a wavelength for the length. The second harmonic mode is a whole wavelength, and this was 3/2 wavelength, and obviously we can keep going on. So what would the pattern be? Lambda is equal to L multiplied by what? If I want to throw an n in here, what do I need to divide n by? N over 2, exactly. That's the and this equation is usually written like this. Lambda sub n is equal to n over 2 times L. Now, we also know that the velocity of the wave on the string, right, is the square root of f over mu, right? And we know v is equal to lambda times f, right? So f is equal to, what, v over lambda? So that means that f is going to be v, which is the square root of f over mu, multiplied by 1 over lambda. So lambda is nl over 2, so 1 over lambda would be 2 over n times l. So that's our frequency. F sub n, the nth mode, has a frequency of 2 divided by n times l multiplied by the square root of f over mu, where this is the velocity of the wave, right? Or, if you look at what f1 is equal to, f sub 1 is just 2 over l, square root of f over mu, and we can write this equation in another way. Let me scroll down just a little bit. We can write it that f sub n is equal to n times f sub 1. I always find this to be a little easier way to do it. Now, what happens when we look at this equation right here? This equation tells us that the frequency that's produced when you strum a string is equal to 2 over ml times the square root of f over mu, right? So what does this mean physically? What happens to the frequency if you shorten the length of the string? Let's say that I tell you I have a frequency, let's say n equal to 1, and I give you that the frequency f1 is 256, right? Hertz, right? And that's for a standard length, right? What happens? I'll pick a length just so that we can use a number, okay? Let's say the length is 1 meter in this case. What happens to the frequency if we still talk about n equal to 1, and I say that L goes to 0.5 meters? What does the frequency become now? We cut the string in half. What happens to the frequency? You get 512, right? 512 hertz. Okay. Now let's turn this into something that you can even try for yourself at home if you want to. So take a string. Fishing line works really well. If you happen to have a guitar or something in your house, that will work really well too. So take a string and fix it at both ends, right? And then what you do is you pluck the string, right? You just pluck it. If you have a string that's really tight, like a piece of fishing line, and you pluck the fishing line, you'll hear a sound come out, right? And then what you do, this really amazed me when I first learned about this. Suppose that you take your finger, right? And you put your finger on the string right here, right? You hold down right there, and you press down on it. And now you pluck just this side of the string here. You pluck this one, right? Compared to the sound that you heard before, right? You're now only vibrating half of the string, right? Before you were vibrating the whole string, right? And according to what we just learned, the frequency that's produced is directly related to the length of that string. So suppose that the first frequency you produced was 256 hertz. By cutting it in half and holding your finger right here and then plucking only one side of it, the frequency doubled. What does that sound like? I bet Kate knows. What's going to be the difference between the sound of the string at 256 versus 512? It's going to be higher pitch, that's right, Andrew? And if you've studied any music at all, you probably know that if this is middle C, oh, you can't see what I'm writing over there, can you? I'll scroll down just a little bit. If this one is middle C right here, right, then 512 is going to be 1 octave. That's right, Kate said it. It's 1 octave above. So even if you don't know anything about musical theory, you probably know that on a piano there's a certain number of keys. There's, I think, 88 keys on a piano. 88 divided by 8 octaves is 8. There's 11 octaves on a piano, right? So those octaves occur for A, B, C, D, E, F, G. Those are the notes, right? The keys. There's like an A key, a B key, a C, A, B, C, up through F. And then it repeats itself, right? So you can start at one point on the piano, like C, and if you count 8 notes higher, that's going to be C again. And you go 8 notes higher, it's going to be C again. I'm doing an awful job of explaining this. My job isn't normally to explain musical theory, but the point is, and this is really amazing, that if you pluck a string and you cut it in half and then pluck just one half of it, the sound is exactly the same note, but 1 octave above it. And that's really fascinating, and it's at the core of how all musical instruments are designed, basically. I'm sure many ancient civilizations learned about this. I first read about it from the ancient Greeks, but I'm sure every single civilization that produced music, it didn't take them long to figure this out. Anyway, so by cutting the string into different segments and plucking it, you can get all types of different sounds out of it, all types of different frequencies, and you can produce the octave that we use in modern music today. Okay, I think we can do this problem now. I think I have 2 problems now that we want to do. Anyone have any questions? I hope you all find this interesting. I wish I could show you a demo of this. I don't have a demo for you. I don't. Oh, we just scroll down. There it is. Boom. Giant bass violin. Okay. In an attempt to get your name in the Guinness Book of World Records. Where did my pen go? Okay. You build a bass viol. A bass viol is like one of those big, tall, stand-up basses where it looks like just like a massive guitar, basically. But, oh, I left out. Okay. I'm sorry. I left something else out. We can do it right here. So we got a second ago that the nth frequency is n over 2l square root of f over mu. I wanted to talk about this equation for just a second again. So we just saw the effect of L. By shortening the string length, you get a higher frequency. What's the effect of increasing the tension? Well, by increasing the tension in the strings, you get a higher pitch. That probably isn't too surprising to any of you that have ever played with a guitar, because guitars at the top right, they have these little knobs like this that are attached to the strings, and you wind them. And by winding them, you can either increase or decrease the tension. And that's how you tune a guitar, right? Is by winding these things that change the tension here. And so you can see that directly inside of this frequency equation is that as the tension goes up, the frequency also goes up, right? Now, another thing you may have noticed on a guitar is that I didn't leave enough room here for me to draw a bunch of strings. Oh, what I could do though is if I zoom in a little bit, I can, not really. So on a guitar, the strings have different thicknesses to them, right? Normally, at least the way that I hold a guitar is like if you're holding a guitar like this, so you're holding it with your right, so you're strumming it with your right hand, you're holding the neck with your left hand, then the string that's on the very bottom is usually really skinny, and the strings that are closer to the top are a lot thicker, right? So can you see why? You have a guitar in your lap right now. That's great. I like that. It's really good. It's a good time during this class to have a guitar in your lap because you can play with it and you can see all these things we're talking about, right? So now if you look at those different size of strings, right? The strings that over here are really skinny, really, really skinny, and the strings out here are a lot thicker. And what's the effect of that, Ryan? If you play these skinny strings compared to the thick strings, what's the difference between the frequency that you hear? Which one's higher, the skinny string or the thick string? So the thick string is deeper, right? These ones here are a lot deeper, right? The thick ones are deeper. And that's exactly what this equation says, right? The mass density is what shows up here, right? That's how thick the string is, right? How much mass per unit length. And so the bigger the thickness, the lower the frequency. If you were to pick up a bass guitars usually have like 4 strings. And I remember the first time I saw a bass guitar, I was at a guitar shop and someone was showing, I didn't know anything about music at all. And I had held a guitar before, but I'd never seen a bass guitar. It really kind of shocked me just how thick the strings on a bass guitar are. The skinniest one on a bass guitar is even thicker than the thickest one on a regular guitar, and that allows for this to be really big, which makes it so you get deep bass sounds, which is exactly what you want out of a bass guitar. Okay, a giant bass viol is just an extreme version of that. It's very, very tall. Why is it tall? Why does it need to be really tall? If you want to produce bass sounds, those are the deep sounds, you want to have a long string, right? Because the longer the string, when this is big, the frequency is small. So that's why these bass viols are huge. In fact, your book actually has a picture of it where it compares it to the size of other types of things. Anyway. That's kind of cool. I should have included I'm gonna show you that picture in a second. Okay, let's do this problem first, though. So it says, in an attempt to get your name in the Guinness Book of Records, you build a base file in with a string length of 5 meters. Okay. What is 5 meters? That's like... It's like a little over 15 feet, right? So this thing would be twice as tall as the tallest person on Earth. A normal human next to this thing would look something like this. These things are really big. They're not this long, though. All right. One string with a linear mass density of 40 grams per meter is tuned to 20 hertz, fundamental frequency. It says this is the lowest frequency that the human ear can hear. We're going to learn more about the range of sounds that we can hear in the next chapter. It says calculate A, the tension in the string, B, the frequency and wavelength on the string of the second harmonic, and C, the frequency and wavelength on the string of the second overtone. Did I tell you that this was the second overtone? I did. Okay. All right. So let's do this. Part A, tension in the string. So what do we know? We know that 20 hertz is the fundamental frequency, okay? So that tells us, the fundamental frequency part tells us that it's n equal to 1. And that means that f sub 1 is 20 hertz. And what we want to solve for is the tension, right? So let's write our equation out. F1 would be 1 divided by 2L. I believe we're given that the length of the strings is 5 meters. And we're also told that the linear mass density, mu, is 40 grams per meter. I'm going to go ahead and convert that to 0.04 kilogram per meter. Okay, so F1 is 1 over 2L, 1 for the n, times the square root of F over mu. And we just want to solve this for the force F, the tension. So we'll get 2L F1 is equal to root F over mu. We'll square out the whole thing. So we'll get 4L squared F1 squared is equal to F over mu. Did I do something wrong here? I guess we just multiply by mu, right? Well, I guess if I did something wrong, we'll check in the units. So mu is 0.04 kg over meter times 4 times L squared. L is 5 meters squared. And then the frequency was 20 hertz. Squared equals the 4. Okay, is this going to work out? Kg over meter cancels out with 1 of the meters. Second, yeah, it works. Okay. So I guess I did it right. I think I did it wrong. Oh, it's because the n's not in there. That's why it looks weird. It would be over n squared, but the n is 1. All right, so we get 0.04 times 4 times 5 times 5 times 20 times 20. So I get 1,600. Pretty sure that's correct. It's the same number we got on Monday. So that's the tension on the string. That's part A. Part B, the frequency and wavelength on the string of the second harmonic. Okay. So let's start with wavelength. So the wavelength, lambda, we said was equal to n L over 2. I'm going to have to scroll back and make sure I'm right about that. Yep. N times L over 2 is the wavelength. So the second harmonic means n equal to 2. So this is just going to be equal to L, so the wavelength is equal to 5 meters. That's easy. The other thing they want us to find is the frequency of the second harmonic. That means we need to find f sub 2. And f sub 2 is equal to n, or 2, times f sub 1. So this is going to be 2 times our original frequency, which was 20. So this is 40. And that sound would be 1 octave above. And finally, in part C, it says to find the frequency and the wavelength of this on the string of the second overtone. And the second overtone is n equal to 3. The first overtone is n equal to 2, second one is n equal to 3. So if we do that, same kind of calculation. So lambda is going to be nL over 2. So that's 3L over 2, which is going to be 3 over 2 times 5 meters. So that's a half times, or 1.5 times 5.
Yeah, that's right, right? So this would be 7.5?
Does that sound right? Any questions? Now, something's wrong with my equation. Two L over N. Yeah. Where did I come up with this equation? N equal to 1, you get L over 2. N equal to 2, you get L. N equal to 3, you get 3 halves L. That looks right. No. It's because this was wrong. This is right. This is right. This should have been 2L over 3, right?
I'm so sorry. This one should be 2L over 3, right? So that our equation is, Sergio's right. This should have been 2L over N. The funny thing is, I fixed it here. Or here. I don't know how I did that. All the rest of the stuff is right. This was the one that was wrong.
Sorry about that. Okay, so going back, this should have been... I don't think it changes this one, because this is going to be 2 and this is going to be N. They're the same thing, so it doesn't really matter. So this one's still going to be right. So this is 2L over N, but N is 2, so this one works out. So it'd be 2L over 2. But this one should have been... So lambda equal to 2L over N. There we go. This should be 2L over 3. So 2/3 of 5. And then this is going to be 3.33. I'm sorry about that. It's been a very long day. All right. There we go. And then we want to find the frequency. F3 is just 3 times F1. So that should be 60 hertz. And there we go. Now things are looking more correct. Yeah. Any questions? Okay, if not, that's where we're going to stop tonight. I find this stuff to be pretty interesting, but also pretty easy to the problems tend to be pretty easy. They can be a little bit tricky, but anyway. That's all for tonight. Stopping the stream. Anyone has any questions, I will stick around.